If the initial mass-energy density of the universe had deviated by just 1 part in 10 to the 60th power, space would have either immediately collapsed in a big crunch or expanded so rapidly that galaxies could never have formed. The very existence of our reality relies on a geometric coincidence that defies all standard probability. Today, precision measurements of the cosmic microwave background prove that our observable universe is perfectly flat. If you were to draw a massive cosmic triangle between distant glowing galaxy clusters, its interior angles would add up to exactly 180 degrees. But maintaining this Euclidean geometry in an expanding spacetime requires a highly unstable equilibrium. The governing mathematics of general relativity demonstrate that any initial spatial curvature should have rapidly amplified, fundamentally warping the universe's geometry over billions of years. To resolve this fine-tuning paradox, cosmologists point to cosmic inflation, a violent, exponential stretch occurring a fraction of a second after the Big Bang that dynamically ironed out the primordial cosmos. Before we can investigate how this inflationary mechanism actually worked, we need to strip away popular misconceptions and define what three-dimensional spatial flatness actually means in physical cosmology. It emphatically does not mean the universe is a two-dimensional disk, like a sheet of paper. In standard Big Bang cosmology, the global geometry of the universe is dictated entirely by its total mass-energy density. Physicists represent this density metric with the Greek parameter omega. General relativity presents 3 distinct spatial possibilities. If omega is greater than 1, space is closed and spherical. If omega is less than 1, space is open and hyperbolic, taking the shape of a saddle. Only when omega equals exactly 1 does the universe possess the critical density required to be perfectly flat. In this precise state, three-dimensional space operates as a strictly Euclidean grid. Beams of light traveling parallel to each other will remain parallel indefinitely, crossing billions of light years without ever intersecting or diverging outward. The cosmological flatness problem, first formally articulated by physicist Robert H. Dicke, during his 1969 Jane lectures, reveals that an omega value of exactly 1 is dynamically unstable. In an expanding universe, omega is constantly being driven away from unity. If the early universe had an omega of 1.0001, that microscopic positive curvature would have compounded exponentially over cosmic time. Before a physical mechanism was discovered, many scientists dismissed the anomaly using the Anthropic principle. They argued that a non-flat universe simply couldn't support the slow formation of stars, galaxies, or observers, meaning we only measure a flat universe because we exist to see it. But a philosophical observation does not satisfy the rigorous physical equations of gravity. Maintaining this critical density today requires far more than just stars, planets, and gas. Ordinary baryonic matter accounts for less than 5% of the necessary mass energy. The universe only achieves its flat geometry when combined with the precise weights of dark matter and dark energy. We observe this precarious balancing act holding steady over 13.8 billion years. So, how do cosmologists actually measure the cosmic microwave background to prove the true shape of space? To measure the true shape of space, cosmologists cannot simply look at local galaxies. They must rely on a fixed cosmic ruler embedded in the cosmic microwave background. This is the residual heat of the Big Bang, a primordial radiation field that captured the exact thermodynamic state of the cosmos just 380,000 years after it was born. This ancient afterglow is not perfectly uniform. It is speckled with subtle temperature fluctuations, microscopic hot and cold spots. Because we understand the fluid dynamics of the early universe, we know the exact physical size these spots had before the universe expanded, which means we can calculate precisely how large they should appear to our telescopes today. This is where the geometry test comes in. Light traveling from that ancient background to Earth has spent nearly 14 billion years moving through the physical fabric of space. If the global geometry of the universe were positively curved, like the surface of a sphere, that intervening space would act as a cosmic magnifying glass, warping the light paths inward and making the spots appear bloated. Conversely, if the universe were negatively curved, often compared to a hyperbolic saddle shape, those light paths would diverge as they traveled toward us. This would compress the incoming light, shrinking the apparent angular size of the spots. Only in a perfectly flat universe, governed by pure Euclidean geometry, would the light beams remain strictly parallel over billions of light years. When the European Space Agency's Planck satellite delivered its definitive mapping of the cosmic microwave background, it measured the position of this first acoustic peak with absolute clarity. The data showed that these primordial temperature fluctuations appear exactly 1 degree across in the night sky. The ancient light has not been magnified by positive curvature, and it has not been shrunk. This observation is the definitive empirical proof of spatial flatness. It tells us that within our observable horizon, three-dimensional space behaves exactly like the grid you learn in high school geometry. The interior angles of a massive, cosmic-scale triangle drawn between Earth and two distant galaxy clusters will always add up to exactly 180 degrees, completely undistorted by global curvature. While a disputed 2019 analysis of a limited data slice suggested a slight positive curvature, modern astrophysics has decisively closed that loop. In early 2026, the Atacama Cosmology telescope released new high-precision polarization maps with noise levels roughly 3 times better than Planck, independently confirming the flat model. When combined with galactic surveys, the observable curvature margin of error is locked at just 0.02%. The empirical measurements have given us their final answer. The universe is geometrically flat. But according to the standard model of Big Bang cosmology, finding a perfectly flat universe after nearly 14 billion years of expansion should be a mathematical impossibility. To understand why, we have to ask a terrifying question. What exactly connects the geometry of space to the mass energy inside it? In the framework of standard Big Bang cosmology, prior to any modern modifications, the geometric curvature of the entire universe is entirely dictated by its total mass energy density. Mass and energy warp spacetime, meaning the collective density of all matter and energy determines whether the cosmos curves in on itself, flares outward, or remains perfectly flat. Cosmologists mathematically represent this critical balance with a single parameter known as omega. It is an exact ratio, comparing the actual density of our universe to a theoretical critical threshold, and it acts as a cosmic time bomb. If omega is greater than 1, the actual density of the universe exceeds that critical threshold. In this scenario, the collective gravitational pull of all matter and energy overwhelms the outward momentum of cosmic expansion. General relativity tells us that this excess mass forces space to curve back on itself, creating a closed spherical geometry. If you fired a beam of light in a perfectly straight line through a closed universe, it would eventually circumnavigate the cosmos and hit you in the back of the head. It guarantees an eventual collapse. Conversely, if omega is less than 1, there is not enough mass and energy to rein in the expanding void. Expansion decisively wins the tug-of-war against gravity, causing the fabric of spacetime to warp into an open, hyperbolic shape, resembling a mathematically infinite saddle. In this open geometry, parallel light beams will rapidly diverge from one another as they travel through the void, spreading apart endlessly. In both of these curving scenarios, The universe's ultimate fate is inextricably tied to its geometric shape, governed by the Friedmann equations. But there is a third, highly precarious option, resting exactly on the knife's edge between these two extremes. If omega is precisely 1, the universe's actual density matches the critical density down to the last decimal point. Here, gravity and expansion are locked in a perfect eternal stalemate, resulting in 0 overall curvature. This is a flat Euclidean geometry, the only configuration where parallel lines remain perfectly parallel across infinite distances. This perfectly flat state is the exact geometric configuration that the Planck satellite measured. Understanding omega as a physical tug-of-war between gravity and expansion reveals why the universe's flat geometry is so incredibly strange. This model assumes a perfectly homogeneous and isotropic distribution of matter on the largest scales, a robust feature of gravity that holds true regardless of the universe's ultimate fate. However, the critical density required to maintain this flat geometry is not a static number. It changes as the universe expands and dilutes over billions of years. Maintaining an omega of exactly 1 requires an active, ongoing physical mechanism. Think of it like trying to balance a pencil perfectly on its sharpened tip. Any microscopic vibration will cause it to fall to one side or the other. In an expanding universe, the value of omega is highly unstable. If omega had been even slightly above or below 1 in the early universe, that microscopic deviation would have grown exponentially over cosmic time, forcing the cosmos into a severe curve. A slightly closed universe would have triggered a rapid collapse. On the other hand, if the initial density had fallen slightly below that critical threshold, the universe would have expanded so aggressively that galaxies, stars, and planets could never have coalesced out of the primordial gas. So, omega must have been exactly 1 at the earliest measurable moment to yield the flat universe we inhabit today. But, as the universe expands, omega refuses to stay put, actively driving the geometry away from flatness. Why did physicists in the late 1960s realize that this delicate balance was a mathematical crisis? By 1969, the mathematical reality of an expanding universe revealed a massive flaw in the standard model of cosmology. Physicist Robert H. Dike demonstrated during his Jane lectures that this delicate tug-of-war over omega is incredibly unstable. If you run the clock forward in a standard matter-dominated or radiation-dominated cosmos, the expansion slows down, causing the critical density to drop faster than the actual physical density of matter. This means that any slight deviation in omega, even a microscopic fraction above or below exactly 1, will amplify exponentially as billions of years pass. Think of omega like a massive pencil balancing perfectly on its tip. If it leans even a fraction of a degree in any direction, gravity will catch it and pull it all the way down, accelerating the fall. In the early universe, if omega had been slightly larger than 1, the extra mass would have halted expansion almost immediately, triggering a rapid and violent gravitational collapse. Space would have folded back in on itself in a catastrophic big crunch before the first stars could ever ignite. Conversely, if the density had been slightly less than critical, the universe would have suffered the opposite fate. Space would have flown apart so fast that the primordial gas clouds could never physically clump together. The expansion rate would have outpaced the gravitational pull of dark matter, leaving a cold void, devoid of galaxies, planets, or observers. Yet, 14 billion years later, our satellite data proves that we inhabit a universe where omega remains essentially indistinguishable from 1. For the universe to still appear practically flat today, DK calculated that the initial density conditions at the Big Bang had to be locked in with impossible precision. Extrapolating the laws of physics back to the earliest measurable moment, known as the Planck time, omega must have been equal to exactly 1 to an accuracy of 1 part in 10 to the 60th power. That is a decimal point, followed by 59 zeros and a 1. It is a level of fine-tuning unseen anywhere else in theoretical physics. To put that scale into perspective, 10 to the 60th power is vastly larger than the total number of atoms in an entire galaxy.
Without a specific physical mechanism driving the initial density to this exact value, the standard Big Bang model required cosmologists to accept an absurdly improbable coincidence. Some researchers attempted to dismiss this fine-tuning problem entirely, arguing it was simply a lucky initial condition of our reality. This philosophical escape hatch, often tied to the anthropic principle, suggested that any other starting conditions would have produced a dead void incapable of supporting life. By this logic, we only observe a flat universe because we wouldn't exist otherwise. But invoking pure luck is fundamentally unsatisfying in empirical science. Dickey's rigorous calculations, published in his 1970 book, Gravitation and the Universe, proved that the baseline mathematical model was missing a crucial dynamical component. The universe is constantly trying to pull away from flatness. The realization that the observed modern flatness requires impossible initial conditions left physicists staring at a cosmos that mathematically should not exist. This anomaly became formally known as the flatness problem, and it remained a glaring hole in cosmology for over a decade.
It proved that whatever happened in the very beginning, it wasn't just a simple outward explosion. What physical event could possess the sheer power to forcibly hammer the entire expanding spacetime perfectly flat in a fraction of a second? In 1981, a proposed modification to the very beginning of the Big Bang provided the exact hammer cosmology was looking for. Theoretical physicist Alan Guth published a landmark paper in Physical Review D, introducing a radical mathematical mechanism called cosmic inflation. Guth realized that the fine-tuning paradox of the early universe didn't mean the equations of general relativity were broken. Instead, it strongly implied that the cosmos must have undergone a brief, intensely violent period of exponential stretching before the standard slower expansion of the universe even began. According to the inflationary framework, this event occurred roughly 10 to the minus 36 seconds after the initial singularity. Driven by a hypothesized scalar field, often referred to as the inflaton field, space itself began to expand at a terrifying, accelerating rate. In a microscopic fraction of a second, the physical volume of the universe was stretched by a factor of at least 10 to the 26th power. This was not a gradual outward drift. It was an exponential snap that fundamentally reset the geometric baseline of the cosmos.
To visualize how this resolves the flatness problem, picture a deflated balloon. Its surface is deeply wrinkled, twisted, and covered in sharp, chaotic curves. If an ant were standing on that rubber surface, the local geometry would feel highly irregular. Now, imagine instantly blowing that balloon up until it is the size of the Earth. The surface directly underneath the ant stretches out so aggressively that to the local observer, it appears to be a perfectly flat plane. The original curvature was not destroyed. It was just mathematically diluted. Cosmic inflation applied this exact same principle to the three-dimensional fabric of spacetime. Whatever primordial curves or chaotic topography existed in the immediate aftermath of the Big Bang were relentlessly ironed out. If the density parameter, omega, was fluctuating wildly above or below the critical density in those first moments, the inflationary epoch acted as an overwhelming physical force.
It suppressed the irregularities and drove the ratio precisely to 1. The exponential expansion effectively wiped the memory of the universe's initial chaotic conditions. Because of this violent stretching, the extreme fine-tuning problem suddenly dissolved. The universe did not need to be miraculously born with a density calibrated to an accuracy of 1 part in 10 to the 60th power. It could have started with almost any random geometry, and the inflationary hammer would still have forced the math into perfect alignment. We observe a flat Euclidean universe today, simply because the space we inhabit was stretched too wide for us to perceive the original curves. Today, cosmic inflation remains the consensus model because it beautifully resolves not just the flatness problem, but also explains the incredible temperature uniformity of the cosmic microwave background. However, the exact nature of the quantum field that triggered this expansion remains entirely unknown to particle physicists. We are heavily relying on a theoretical mathematical mechanism because it so cleanly fits our observational data. But relying on an unverified epoch makes some modern cosmologists uncomfortable. If the physical trigger for inflation cannot be found, it forces us to reconsider the foundations of the Big Bang itself. If we strip away the inflationary iron, we're back to staring at an impossibly precise mathematical coincidence. This lingering uncertainty has prompted some physicists to search for alternative frameworks to save the standard model. Are there other ways to organically grow a perfectly flat universe? Or are we simply the lucky survivors of a cosmos that just happened to avoid collapse? If cosmic inflation was the violent hammer that flattened reality, what if no hammer was ever needed? Because the exact quantum field that caused inflation remains unproven, some physicists argue we might be looking at the problem backward. Long before the inflationary paradigm took hold, cosmologists like Margaret Geller suggested the flatness problem was a philosophical illusion rather than a physical one. They pointed to the Anthropic principle, a highly debated framework stating that the universe is flat simply because we are here to measure it. According to this anthropic selection, if the initial mass-energy density wasn't balanced on that exact razor's edge, we would not exist to ask the question. A slight deviation would have caused space to collapse immediately or blow apart so rapidly that galaxies never formed. Observers can only evolve in stable, flat universes. However, to many theoretical physicists, leaning on anthropic chance feels less like an answer and more like surrendering the search for a rigorous physical mechanism. That frustration led to the development of modern, competing physical models, most notably bouncing cosmologies like the ekpyrotic universe. Championed by physicists Paul Steinhardt and Neil Turok, this theoretical framework attempts to bypass the need for a rapid inflationary burst entirely. Instead of our universe bursting out of an infinitely dense singularity, the cyclic model argues that space undergoes endless epochs of expansion and contraction. In a cyclic universe, the extreme fine-tuning of spatial geometry happens in reverse. Before the Big Bang ever occurs, a slow, grinding contraction phase lasts for trillions of years. This prolonged shrinking acts like a cosmic steamroller, naturally compressing and smoothing out any warps or curves in spacetime. By the time the universe shrinks down and bounces back out, its geometry has already been driven perfectly flat. These alternative theories remain actively debated because the absolute flatness of our universe is constantly being stress-tested by new observations. In 2019, a minority research paper analyzed a specific slice of data from the Planck satellite and made a controversial claim. They argued that the cosmic microwave background actually hinted at a universe that is slightly closed, curving back onto itself like a hypersphere. If space was definitively proven to be closed, it would severely threaten the standard inflationary model. But that 2019 claim was fiercely disputed. When astrophysicists combined the Planck data with measurements of baryon acoustic oscillations, the rippling structures of galaxies across the universe, the apparent curvature vanished. The combined datasets rigidly constrained the geometry parameter back to 0, confirming that the flat model remains statistically dominant. While models like the ekpyrotic bounce struggle to match the precise temperature fluctuation data as cleanly as inflation does, they uphold a vital scientific rigor. They prove that explaining the spatial geometry of the universe is still an active testing ground for fundamental physics. Whether our reality was flattened by a rapid stretch or an incredibly slow trillion-year contraction, the end result is a cosmos balanced perfectly on the brink. But acknowledging that the universe is flat only introduces an even more terrifying physical reality. If the parameter omega is flawlessly balanced at exactly 1, ordinary matter cannot explain the math. All the visible atoms, stars and galaxies, account for less than 5% of the required density. So, where is the invisible mass hiding in the dark to keep our universe from tearing itself apart?
If cosmic inflation was the mechanism that forcefully flattened the early universe, the modern cosmos relies on an immense, invisible weight to keep it that way. In standard cosmology, spatial flatness is not just a relic of the Big Bang. It requires an active, ongoing physical balance to prevent the fabric of space from warping today. To maintain a perfectly Euclidean geometry, the universe's total mass energy density, the value we call omega, must equal exactly 1. But when astronomers take a census of all the ordinary baryonic matter in the cosmos, every star, planet, dust cloud, and black hole, it is drastically inadequate. Ordinary matter accounts for less than 5% of the critical density required to keep space flat. If ordinary matter was all the universe contained, space would be severely open and saddle-shaped. It would expand so rapidly that gravity could never pull gas together to build a single galaxy. To close the geometric gap, we must factor in dark matter. Mapped through the gravitational lensing of distant starlight and the fast rotation of galaxies, this invisible framework adds roughly 27% to the total density.
Yet, even with all the dark matter in the cosmos, we only reach about 1/3 of the required cosmic weight. The observable universe only achieves a perfectly flat geometry when we add the final, most massive component, dark energy. Making up roughly 68% of the cosmic budget, this repulsive force fills the remaining gap. As confirmed by the early 2026 legacy data from the Dark Energy Survey and the Dark Energy Spectroscopic Instrument, it is only this exact trio, 5% ordinary matter, 27% dark matter, and 68% dark energy, that pushes omega to exactly 1. It acts as the final weight on the cosmic scale. This delicate equation is the bedrock of the lambda CDM model, the standard model of Big Bang cosmology. Dark matter and dark energy are not optional theories used merely to explain missing galactic mass or the accelerating expansion of space. They are mathematically required to make the geometric shapes we observe actually work.
If upcoming astronomical surveys ever demonstrate that the combined sum of matter and energy falls significantly short of 1, our entire understanding of cosmic geometry and the age of the universe itself would fundamentally break down. But there is a lingering, crucial uncertainty. When cosmologists say the universe is completely flat, they are speaking with absolute precision only about our local, observable horizon. Measurements from the European Space Agency's Planck satellite constrain the spatial curvature to effectively 0, within a margin of error of just 0.2%. However,
The inflationary model predicts that the observable bubble was stretched so vastly that the true unobservable global topology of the universe could theoretically still harbor a slight hidden curvature far beyond our sight. Regardless of whether you accept cosmic inflation or prefer alternative cyclic models, the reality of a flat universe forces us to rely entirely on an invisible dark sector. Our equations demand a dark universe simply to make the fundamental three-dimensional geometry of reality work. But confirming the exact mechanism that originally flattened it requires looking deeper than today's galaxy distributions. To truly close the book on the flatness problem, we must find the physical scars of the stretching itself. And astronomers are now building the exact instruments to hunt for the primordial echoes of that original hammer. The search for primordial gravitational waves will ultimately reveal if our universe was violently stretched into its flat shape, or if an even deeper mechanism is at play. In the Standard Model, if cosmic inflation actually happened 10 to the minus 36 seconds after the Big Bang, that violent exponential expansion would not have been entirely silent. It would have generated massive, universe-spanning ripples in the fabric of spacetime, permanently altering the underlying geometry. It is crucial to distinguish these from the gravitational waves detected by modern observatories like LIGO, which are produced by local recent events like merging black holes. Primordial gravitational waves are a global background hum. As they squeezed and stretched the ultra-hot plasma of the early universe, they should have left a specific permanent imprint on the cosmic microwave background, the oldest light we can see. Physicists call this targeted physical signature primordial B-mode polarization. It manifests as a faint, twisting pinwheel-like pattern in the polarization of the CMB. Because only a violent, rapid stretching of spacetime can theoretically produce these specific twists on such massive scales, detecting them would serve as the ultimate smoking gun for the inflationary epoch. To finally capture that signal, cosmologists are designing next-generation instruments with extreme sensitivity. As of 2026, major ground-based efforts have consolidated in the high-altitude Atacama Desert in Chile, utilizing telescope arrays that map the sky through the planet's thinnest atmosphere. Concurrently, the Japanese-led Lightbird satellite is finalizing its mission definition, preparing to launch into deep space to survey the entire sky free from atmospheric interference. But finding this twisting signature requires pushing our engineering to absolute limits. The primary obstacle is ordinary interstellar dust floating within our own Milky Way galaxy. This dust naturally aligns with galactic magnetic fields and can perfectly mimic the primordial B-mode signal, a complication that notoriously led to a massive false alarm during the BICEP 2 experiment. To prove inflation, the new telescopes must observe across up to 15 different frequency bands simultaneously. By comparing how the signal changes at different frequencies, physicists can meticulously map and subtract the foreground dust, isolating the true cosmic background. If the B-modes survive that extreme filtration, inflation moves from a brilliant hypothesis to an established historical fact. Conversely, if these new observatories search the sky and find absolutely no primordial B-modes at the predicted tensor to scalar ratios, the implications would be staggering. A definitive null result might effectively rule out the most dominant inflationary models. This would heavily favor alternative explanations, such as cyclic or bouncing cosmologies, which can produce a flat universe without generating these massive gravitational waves. Until those ancient echoes are either found or definitively ruled out by the upcoming data, the perfect geometric flatness of our cosmos remains a quiet, enduring monument to the unknown. The fact that the observable universe walks an exact tightrope of critical density, maintained only by a vast, invisible ocean of dark energy and dark matter, is one of the most magnificent mathematical achievements in modern physics. It is an impossible coincidence that points directly back to the absolute extreme forces present at the dawn of time.